Hello, class. Today we're going to be talking about light waves, and so you have some notes to take and some the worksheet to follow along with. After this, you're going to be doing a lab called Waves on a String, which will allow you to manipulate some of the different characteristics of a wave and see how that affects things. And so, as we go through it today, I apologize for being stopped up in the raspy voice. But we'll work through it as we get through this information. So we've already talked about sound waves and some of their characteristics, and light waves and sound waves share some characteristics, but then on others, they have some different ones. And so let's look at some of those things. Light is a form of radiant energy known as the electromagnetic spectrum or electromagnetic radiation. And so you see an example here of the electromagnetic spectrum. We're going to talk more about that in future lectures, but you can just got to get a picture of what it looks like here. Unlike sound waves, electromagnetic waves do not have to travel through matter or a medium to exist. And so you see that that's the sun shining light on the earth there. That's how the sunlight's able to get here. Is it doesn't need particles or molecules the way that sound does. Electromagnetic waves travel in straight lines in the form of transverse waves. And so if you remember our demonstration using the rope for transverse waves, as you move your hand up and down, the waves move up and down. And so they're transverse, moving perpendicular to the resting point. So the energy is moving in this direction, but the wave is moving up and down as well. So because of these different names, there's two other things light waves can be called. You may hear of them called the electromagnetic waves. You may hear of them called transverse waves. And so just like sound had a couple of other names that you would have to go by, light does as well. And so you may hear any of these. It's all talking about the same type of wave for our class. So all transverse waves or light waves or electromagnetic waves have the basic same components. They have a crest, a trough, wavelength, amplitude, and frequency. And so for the remainder of our lesson today and what you're going to be working with when you do the waves on a string are these five characteristics of a transverse wave. So let's look at those. The crest is the highest point on the wave. And so this very top piece there is referred to as the crest, and then the trough down here at the bottom. This line across the middle is the resting point. If that were a rope and were pulled tight, that's where it would land. And so the crest is the highest point above the resting point. The trough is the lowest point below the resting point. And then wavelength is just the distance from one crest to another. So in a sound wave, you're measuring compressions and rarefactions. In a light wave or transverse wave, I think it's a little easier to measure because you just measure from the top of one to the top of the other. You can also do from the bottom of the trough to the bottom of the next trough. But basically, you're just measuring where it repeats. And so even here on this side where you have a trough and it goes up to the crest, back down to the trough. And so that would be one wavelength. If you were measuring in the middle, you could even do that, and it would go through a trough, through a crest, back to the middle. That would be a wavelength. Anywhere where the wave repeats itself. And so this part, it's going down, it comes back up, and right where it goes down again would be a wavelength, or the tops or the bottoms. And we talked about amplitude. Amplitude in a light wave is measured a little differently than it was in a sound wave. In a sound wave, it's how tight that compression is together. In a light wave, it's going to be from the resting point, from this middle line, up to the highest point or to the lowest point. Where people get confused is they want to measure from the lowest point to the highest point. That would actually be double your amplitude. You want to measure from the middle line to the highest point or from the middle line to the lowest point. But the middle line will be your starting place all the time. the greater the amplitude, the taller the wave is going to be, and the more energy it's going to carry. And so, just like in a compression wave, how much amplitude there is determines the energy. Same with a light wave. It's just measured differently because the waves interact differently. So take some time now and go ahead and draw and label a transverse wave on your worksheet. Make sure you get where the crests are, where the trough is. Go ahead and draw in the resting point, this middle line, so that you can show the amplitude. And so try to draw that as evenly as you can. It doesn't have to be perfect, but just so you can get a picture of that. And then the wavelength, where the wavelength would be. Draw a wavelength measurement at the top and one at the bottom. And so you can see that those are in both places there. When we talk about frequency in light waves, it's the same basic idea as in a sound wave, just because you measure some of those things a little bit differently. I think it's a little bit easier to see in a transverse wave. And so frequency is the number of waves produced in a given amount of time. And so when we measure it, we're measuring it in how many wavelengths go through a specific point in 1 second. And we measure this in hertz. So if we look at our video here that we have, and you see that transverse wave is moving. Now, a couple of points to point out. Notice each individual spot is not moving down the wave. It's just moving up and down, and then the energy is being carried across. But in our wave here, if we pause it and we count the wavelengths, let's assume that this whole section is 1 second in time. And so we start here at a crest, and we would measure to the next crest. So that's 1, 2, 3. And so in that second, 3 wavelengths went by. You just measure from crest to crest. So 1, 2, 3. So that would be a frequency of 3 wavelengths over 1 second, which would be 3. It would be 3 hertz. Of course, on our video here, it's not really ever going to change. That one's a pretty consistent one. But no matter where we stop it, it's going to be about the same. You see that point there. You come across to the same point. 2, 3. It's going to be 3 hertz. And so in most of the measurements we're going to do, it's always the picture is going to represent 1 second in time. And you would just count how many wavelengths there are to know the frequency. You'll get some practice in doing that next week. Frequency and wavelength in a transverse wave or a light wave, same relationship as what it has in a sound wave. It's an inverse relationship. That means when one goes up, the other one goes down. That means that the wavelength increases, frequency decreases. Or when frequency increases, wavelengths decreases. So you see in our picture here, if it's a wide wavelength, and so the length here is much longer than it is over here, the frequency is going to be low. Frequency is just how often wavelengths are happening in that second. So if these are both the same amount of time, both these pictures, over here, you would have 1, 2 wavelengths. So it'd be a frequency of 2, where here you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a frequency of 10. And so as the wavelength increases, the frequency would decrease. And the opposite's true too. When the frequency increases, the wavelength decreases. Today you're going to be doing a lab called Waves on a String. And so you're going to open up a simulator that's going to look like this. You see down here, it has places for you to adjust amplitude and frequency, dampening and tension. It has a ruler tool that you could click on, and a ruler will pop up on the screen, a timer here that you can use. And so the reference lines that we'll put in there. Up here, you can set it on manual or oscillate. Oscillate, it's going to go up and down on its own. Manual, you would have to click and drag and move it around. Over here, a fixed end, which is what it's set at right now. A loose end, which would take away this clamp, and it would just be like a string that would be loose, and no end. It actually pops up a window and it goes out the window. And so you can see how the wave changes based on these different settings. You're going to start off just playing around with it. Do some different things. Check out the different ways you can set it up, how that impacts the wave. What you're going to see is when it has this fixed end, you're going to have interference as the wave bounces back and forth. When you have a loose end, it's not going to do that. And so it's just going to kind of flap like in the wind. But you'll be able to play around with it a little bit. But then there's some specific things for you to do in the lab. So you'll need to get a lab sheet from the teacher and then work your way through the lab. Make sure you follow directions carefully. There's graph paper on the teacher's desk for some of the stuff that you'll need to do, and that will be taken up for a grade. So make sure you take your time, work through this. If you don't get it all done in class, you can do it for homework, and I'll be collecting that on Monday. So if you have questions you don't fully understand, do the best that you can. Recognize that I'm not there today to help you through stuff, but work through it the best you can. And then as long as we see that you're putting effort in, you'll be okay as far as the lab grade. So take your time, work through the lab today, and I will see you on Tuesday because we're off on Monday.